February 21, 1940. A small laboratory at Birmingham University in England. Two engineers are about to switch on a device they've been building in secret for 3 months. A device carved from a copper block using gun manufacturing jigs borrowed from a Colt revolver factory. They don't know if it will work. Their boss thinks it's a long shot. The military officials funding them are getting impatient. Britain is at war, and they need results. John Randall flips the switch. The device hums to life. And in that moment, everything changes. Not just for them, not just for Britain, but for the entire outcome of World War II. This device, no bigger than your fist, would do something impossible. It would generate 400 watts of microwave energy at a wavelength thought to be unachievable. Within months, they'd push it to 10 kilowatts, then 25 kilowatts, then over 100 kilowatts. And here's the crazy part. 1 year later, the Americans would call it the most valuable cargo ever brought to their shores. More valuable than any weapon. More valuable than gold. More valuable, they said, than even the plans for the atomic bomb. This is the story of how one radical engineering design turned Nazi U-boats blind in the Atlantic Ocean. How it saved Britain from starvation. How it changed the course of the war. And how it ended up in your kitchen, cooking your dinner every single night. To understand why this device mattered, you need to understand just how desperate things were in 1940. Britain was an island under siege, not from bombs alone, but from something far more deadly: hunger. Every week, hundreds of cargo ships crossed the Atlantic, carrying food, fuel, oil, weapons, and everything Britain needed to survive. These weren't luxury items. This was survival. And beneath the waves, hunting in packs like wolves, were Admiral Karl Dönitz's U-boats. Dönitz had developed a tactic that was devastatingly effective. Instead of operating alone, his submarines hunted in coordinated groups called wolf packs. 6 boats, 10 boats, sometimes 20 or 30 boats stretched across a convoy route like a deadly net. Here's how it worked. A single U-boat would spot a convoy of Allied merchant ships steaming across the Atlantic. That U-boat wouldn't attack immediately. Instead, it would radio the position back to headquarters in occupied France. Dönitz would then coordinate every U-boat in the area, directing them to converge on that convoy. Then, when darkness fell, the wolf pack would strike from multiple directions simultaneously. Surface under cover of darkness. Fire torpedoes. Dive before the escorts could respond. Repeat. The results were catastrophic. In September 1940, convoy HX-72 lost 11 ships in just 2 nights. 42 merchant vessels went in. Only 31 came out. In October, convoy SC-7 was devastated. 20 ships sunk out of 34. 2 nights later, convoy HX-79 lost 12 more. The numbers tell the horror story. In 1940, U-boats sank over 2 million tons of Allied shipping. In 1941, over 2.1 million tons. In 1942, as America entered the war and more convoys sailed, U-boats sank a staggering 6.2 million tons. Ships were being sunk faster than they could be replaced. Supplies were dwindling. Food rationing in Britain got tighter and tighter. Churchill himself would later write that the U-boat peril was the only thing that ever really frightened him during the entire war. And Admiral Dönitz was supremely confident. He famously declared, "An aircraft can no more kill a submarine than a crow can kill a mole." He believed submarines were essentially invulnerable when operating at night on the surface. And he was mostly right. The Allies had radar, yes, but their radar was primitive. The chain-home system protected Britain from German bombers using massive towers that could detect aircraft 100 miles away. But those systems used radio waves with wavelengths between 10 and 13 meters. Great for seeing bomber formations. Useless for spotting the tiny conning tower of a surfaced submarine. The British had developed airborne radar too. The ASV Mark I and Mark II systems used shorter wavelengths, around 1.5 meters. Aircraft could mount these systems and patrol the shipping lanes. But there was a problem. The Germans had developed a simple receiver called METOX. U-boats could detect ASV radar signals from far beyond the range at which the radar could detect the submarine. The METOX gave U-boats plenty of warning. Dive. Wait for the aircraft to pass. Surface again once it was gone. By late 1942, U-boats carried METOX as standard equipment. ASV Mark II became essentially useless. It wasn't finding submarines. It was just warning them that an aircraft was nearby. The Atlantic was becoming a killing field. Britain was running out of time, running out of food, running out of fuel, running out of hope. Something had to change. Something radical. Something the Germans wouldn't expect and couldn't detect. The solution was already being built in that small laboratory at Birmingham University. But to understand what Randall and Boot created, we need to understand what made their device so revolutionary. Let's step back to 1939, September. Britain has just declared war on Germany after the invasion of Poland. At Birmingham University, Professor Mark Oliphant runs a classified radar research program funded by the British Admiralty. Oliphant is an Australian physicist who's brilliant, driven, and not afraid to pursue crazy ideas. That summer, before the war started, Oliphant had visited one of the chain-home radar stations with two of his young researchers, John Randall and Harry Boot. They saw the massive towers, the huge antennas, the enormous machinery required to generate and detect radar signals. Oliphant had a vision. He wanted radar that could fit in an aircraft, radar that could see fine details, not just big bomber formations, radar that could spot a submarine's conning tower in darkness or fog, radar that could map the ground below for navigation and targeting. To achieve this, they needed shorter wavelengths, much shorter, 10 centimeters or less. That would give them the resolution they needed and allow for smaller, lighter antennas that could actually fit on a plane. The problem? Nobody knew how to generate high-power microwaves at that wavelength. There were two approaches in 1939. You could build a low-power oscillator and amplify the signal using a klystron, which was a specialized vacuum tube. Oliphant tried this. He managed to generate 400 watts at 10 centimeters. But the klystron was bulky, fragile, and couldn't be easily sealed for field use. It wouldn't work in combat conditions. The second approach was to build a high-power oscillator that generated the microwave signal directly. This required something called a magnetron. Now, magnetrons weren't new. An American engineer named Albert Hull had invented the basic magnetron concept back in 1921 while working at General Electric. Hull was trying to get around a patent on the triode vacuum tube, and he came up with this alternative design that used a magnetic field to control electron flow instead of an electric field. Hull's magnetron worked, but it was incredibly inefficient. Only about 30% of the energy put in came out as usable radio waves. Not good enough. Over the years, researchers in Germany, Russia, Japan, France, and the Netherlands had all experimented with magnetron designs. Some had even tried adding resonant cavities to improve efficiency. Patents were filed. Papers were published. But nobody had managed to build a magnetron that could generate kilowatts of pulsed power at centimetric wavelengths in a compact, reliable, mass-producible package. Nobody thought it was possible. Except Randall and Boot. John. Randall was 35 years old. In 1939, he'd studied physics and had worked on various electronics projects. He was methodical, careful, and had a knack for seeing elegant solutions to complex problems. Harry Boot was younger, 29, and had recently joined Oliphant's team. He brought practical engineering skills and wasn't afraid to try unconventional approaches. In November 1939, Randall had an epiphany. He'd been reading an old book he'd picked up during a holiday in Wales, a translation of Heinrich Hertz's 1890s work on electric waves. Hertz had used simple resonant wire loops to generate and detect radio waves. Randall thought, what if we built a three-dimensional version of those loops? What if we surrounded a magnetron cathode with cylindrical resonant cavities, sized precisely to resonate at the wavelength we want? It was a radical idea. The cavities would be machined directly into a copper block. The dimensions of the cavities would determine the frequency. No external circuits, no adjustments, just pure, elegant physics. Boot immediately saw the potential. They sketched designs. They did calculations. They realized they could use manufacturing jigs from a Colt revolver factory to machine the cylindrical cavities because the dimensions were similar. In late November 1939, they showed their first copper block prototype to visitors, Lawrence Bragg and Edward Appleton, two of Britain's most distinguished physicists. The visitors were intrigued but skeptical. Could this thing actually work? Randall and Boot spent December 1939 and January 1940 building their prototype. They designed a device with 6 cylindrical cavities arranged in a circle around a central cathode. Each cavity was connected to the central chamber by a small slot. The theory was elegant, but untested. When electrons from the heated cathode would spin in the magnetic field, they'd pass by these slots. If the dimensions were right, the electrons would excite resonant oscillations in the cavities. Those oscillations would feed back and organize the electron stream into bunches. Those bunches would deliver energy to the microwaves building up in the cavities. A feedback loop. Self-sustaining, self-amplifying. If it worked, they machined the copper block. They assembled the cathode. They connected the vacuum pump. They installed the magnets. February 21st, 1940. Everything was ready. They turned it on, and it worked. Not just worked. It sang. The device generated 400 watts of continuous microwave power at 9.8 centimeters wavelength, 10 times more efficient than a klystron, small enough to hold in your hand, operating at exactly the frequency they'd designed it for. Randall and Boot were stunned. They'd expected something, but not this. Not on the first try. They immediately reported their results to Oliphant, who was equally astonished. This was a genuine breakthrough. This could change everything. But there was a problem. The device they'd built was a laboratory prototype. It needed a vacuum pump running constantly. It had frequency instability issues. It couldn't survive field conditions. To turn this into a practical weapon, they needed engineers. They needed manufacturing expertise. They needed it fast. The Admiralty moved quickly. In April 1940, just 2 months after the successful test, they signed a contract with the General Electric Company at Wembley in London. GEC had a team of experienced engineers led by Eric Megaw, who'd been working on magnetrons for 5 years. Megaw looked at the Birmingham prototype and immediately understood both its brilliance and its limitations. He and his team got to work redesigning it for field use. First, they changed the cathode design, using a thoriated tungsten spiral that could withstand higher temperatures and last longer. Second, they sealed the entire device in an all-metal housing that didn't need external vacuum pumps. Third, they added 2 more cavities, going from 6 to 8, which improved the power output. Fourth, they minimized the air gap for the magnet, allowing them to use a compact permanent magnet instead of bulky electromagnets. By June 1940, the GEC team had done it. Their redesigned magnetron generated 3 kilowatts of pulsed power. Within weeks, they pushed it to 10 kilowatts. By September, 25 kilowatts. By 1941, over 100 kilowatts. And the device was rock-solid reliable, sealed, compact, ready for mass production. But there was still a problem. The frequency would wander. The magnetron could oscillate in different modes, jumping between frequencies unpredictably. This made it difficult to tune receivers and reduced overall performance. Enter James Sayers. Sayers was another member of Oliphant's Birmingham team. He'd previously worked on vacuum tube design and understood the physics of cavity resonators intimately. In August 1941, Sayers suggested a brilliantly simple solution: strapping. He proposed connecting the cavities with metal straps in a particular pattern. These straps would constrain the oscillations to a single mode, preventing the frequency from wandering. It was elegant, simple to manufacture, and it worked perfectly. With Sayers' strapping innovation, the cavity magnetron became not just powerful, but also stable and predictable. It was ready for war. By August 1940, Britain had a problem and a solution. The problem? Britain was fighting alone. France had fallen. The Germans controlled most of Europe. Britain was under constant air attack and naval blockade. Resources were scarce. Manufacturing capacity was stretched to the breaking point. The solution: the cavity magnetron. A device so advanced that it could revolutionize radar, turn the tide of the Battle of the Atlantic, and give the Allies a decisive technological advantage. But Britain couldn't mass-produce magnetrons fast enough. The factories were building Spitfires and bombs and tanks. There wasn't capacity to ramp up production of a completely new technology. America had the capacity. But America wasn't in the war. President Roosevelt was sympathetic but constrained by isolationist sentiment in Congress. He couldn't just give Britain unlimited military aid. Winston Churchill's scientific advisor, Henry Tizard, had a radical idea. What if Britain shared its most advanced military technologies with America? Not just shared the concepts, but gave them actual working prototypes and all the technical details? In exchange, American industry could manufacture these devices at scale. America would benefit from the technology. Britain would benefit from American manufacturing capacity. It was an unprecedented proposal. Countries don't just give away their most classified military secrets. But these were desperate times. Churchill approved the plan. In September 1940, Henry Tizard led a small delegation to America. They carried with them a black tin trunk. Inside that trunk were blueprints, prototypes, and technical documents representing Britain's most advanced weapon systems. Proximity-fused. Shells that could detect and explode near their targets. Jet engine designs. Designs for processing uranium for atomic weapons. And magnetron number 12. The 12th magnetron built by GEC, capable of generating 10 kilowatts at 10 centimeters wavelength. The delegation met with American military officials and scientists in Washington, D.C. At the Wardman Park Hotel. When the discussions turned to radar, the Americans described their problems. Their Klystrons could only produce 10 watts of microwave power. They'd hit a wall. They couldn't see a way forward. One of the British delegates, a Welsh physicist named Edward Bowen, reached into his briefcase. He pulled out the magnetron. He set it on the table. He explained what it could do. The Americans were speechless. A report from that meeting recorded, "The atmosphere was electric." The U.S. experts found it hard to believe that such a small device could produce so much power, and that what lay on the table in front of us might prove to be the salvation of the Allied cause. Bell Labs tested the British magnetron. It produced 1,000 times more power than the best American devices. Not 10% more, not twice as much, 1,000 times more, at 5 times the frequency. It was like showing engineers in the age of candles a working electric light bulb. The American historian James Finney Baxter later wrote, "When the members of the Tizard mission brought one cavity magnetron to America in 1940, they carried the most valuable cargo ever brought to our shores." The Americans moved fast. By October 1940, MIT had established the Radiation Laboratory, deliberately named to sound like a nuclear research facility to confuse spies. The Rad Lab's sole purpose was to develop radar systems based on the cavity magnetron. Bell Labs began copying and improving the British design. By December 1940, they had working prototypes. Within months, American factories were producing thousands of magnetrons. Over the next 5 years, the MIT Rad Lab grew to employ nearly 4,000 people. They developed over 150 different radar systems. Every major Allied radar system used cavity magnetrons, the crazy device that Randall and Boot built in that Birmingham's laboratory had become the foundation of Allied radar superiority. Now, it needed to prove itself in combat. Remember Donitz's confident declaration? An aircraft can no more kill a submarine than a crow can kill a mole. By March 1943, he was about to learn how wrong he was. The new centimetric radar systems started deploying in late 1942 and early 1943. The ASV Mark III used magnetrons to generate radar pulses at 10 centimeters wavelength. The H-2S ground mapping radar operated at 9 centimeters. These systems were revolutionary for several reasons. First, the shorter wavelength meant much better resolution. ASV Mark III could detect a submarine's conning tower from miles away, even in darkness or fog. It could distinguish between different objects, not just sea blobs. Second, the wavelength was short enough that the antennas could be compact and lightweight. They fit inside aircraft nose cones. They could be rotated to scan in all directions. Some systems used a small rotating dish that gave a map-like display of everything around the aircraft. Third, and most importantly, the Germans couldn't detect them. Remember the METOX receiver that had made ASV Mark II useless? METOX was tuned to detect the 1.5-meter wavelength of the old radar. It was completely blind to the 10-centimeter wavelength of the new magnetron-based systems. When ASV Mark III started operating, U-boats were suddenly getting caught on the surface with no warning. Aircraft would appear out of the darkness and attack before the U-boats could dive. U-boat crews were baffled and terrified. RAF Coastal Command started using a particular tactic that was devastatingly effective. They knew from broken Enigma intercepts where the U-boat bases were, heavily fortified submarine pens on the Atlantic coast of occupied France at Brest, Lorient, La Rochelle, and Bordeaux. They also knew that U-boats had to surface regularly to recharge their batteries using diesel generators. This required running on the surface for hours, usually under cover of darkness, when they thought they were safe. Coastal Command aircraft would patrol the approaches to these bases at night using ASV Mark III radar. When they detected a surfaced U-boat, they'd attack immediately with depth charges and machine guns. U-boats were being sunk, coming into and leaving their own bases. What should have been the safest part of their patrol became a killing zone. In the open Atlantic, the combination of new technology was overwhelming. Long-range aircraft with ASV Mark III could patrol vast areas. When they found a U-boat, they could track it continuously. Escort carriers could launch aircraft to support convoys directly. Surface escorts used new centimetric surface search radars. The Allies also had something else: broken codes. Bletchley Park had cracked the German naval enigma. Ultra-intelligence told the Admiralty where the U-boat wolf packs were forming. Convoys could be routed around the wolf packs, or support groups could be sent to hunt them. May 1943 became known as Black May in the German submarine service. In that single month, 41 U-boats were sunk. 41 submarines with all their crews lost in just 30 days. That represented 25% of the operational U-boat fleet. For context, in the entire year of 1940, Germany had lost 24 U-boats total. In May 1943 alone, they lost 41. The kill ratio had inverted catastrophically. U-boats were being sunk faster than they could be replaced. More importantly, experienced crews were being lost. The new crews that replaced them had less training, less experience, and shorter life expectancies. On May 24, 1943, Admiral Dönitz made a decision that must have been agonizing. He ordered the U-boats to withdraw from the North Atlantic. The Wolfpack offensive that had nearly starved Britain into submission was over. Dönitz tried to resume operations later in 1943 with upgraded U-boats carrying better defensive equipment. But the technology gap never closed. The Allies kept improving their radar systems. They developed better tactics. They trained more crews. U-boat losses continued to mount. In 1943, 244 U-boats were sunk. In 1944, 245 more. In 1945, even as Germany collapsed, they lost 153 more U-boats. The casualty rate for U-boat crews was horrific, 70%. Out of 41,000 men who served in U-boats during the war, 30,000 died and 5,000 were captured. Only 6,000 survived. The Battle of the Atlantic turned decisively in favor of the Allies. By 1944, supplies were flowing across the Atlantic in unprecedented volumes. The build-up for D-Day couldn't have happened without winning the Battle of the Atlantic first. And the weapon that turned the tide wasn't a bigger gun or a faster ship. It was a fist-sized copper device that made submarines visible in the dark. Here's the thing that makes this story even more remarkable. The Germans knew about cavity magnetrons. When a British bomber carrying an H-2S radar crashed near Rotterdam in February 1943, German technicians recovered the equipment intact. The self-destruct charges had failed. The Germans got their hands on a complete magnetron-based radar system. They brought it to Telefunken, their electronics company. Engineers examined it carefully. They recognized the cavity magnetron design immediately, because they'd seen it before. Russian scientists, Alexeyev and Malyrov, had published a paper on cavity magnetrons in 1936. German scientists were aware of this work. They'd even discussed it. Japanese engineers had built their own version in 1939. The German reports after examining the British. Magnetron noted that similar designs had been independently developed in multiple countries. So, why didn't the Germans build their own centimetric radar before the British? Why did they fall so far behind in radar technology despite being leaders at the start of the war? The answer is both simple and tragic. Hitler made a catastrophic strategic decision. After the fall of France in June 1940, Hitler was supremely confident. Germany controlled most of Europe. Britain was isolated. The Soviet Union was not yet in the war. Victory seemed inevitable. In this moment of hubris, Hitler issued an order. No scientific research was to be undertaken unless a conclusive result could be guaranteed within 1 year. Think about what this meant. Long-term research projects were cancelled. Basic research was defunded. Scientists were told to focus only on incremental improvements to existing weapons. This order strangled German technological development. It prevented the kind of breakthrough research that produced the cavity magnetron. It created a culture where scientists were afraid to propose ambitious projects that might not succeed quickly. Hermann Göring, head of the Luftwaffe, reinforced this mindset. He didn't believe radar would have much impact. He didn't think the Allies could develop anything significantly better than what the Germans had. He was catastrophically wrong. The British approach was the opposite. Even when Britain was fighting for survival in 1940, they continued funding ambitious research projects. They took risks on ideas that might fail. They encouraged scientists to think big. And then they did something even more remarkable. They shared their breakthrough with America, even though America wasn't in the war yet. That kind of strategic thinking, that willingness to take risks and collaborate, made all the difference. By the time Germany realized their mistake, it was too late. They tried to copy the British magnetron, and they succeeded in making a working replica. But deploying it required redesigning their radar systems, retraining their operators, and manufacturing thousands of units. They never caught up. The Germans lost the technological race not because their scientists were less capable. They lost because their leadership made terrible strategic decisions about how to support scientific research. The story doesn't end in 1945. One day in 1945, An American engineer named Percy Spencer was working at Raytheon Corporation in Massachusetts. Raytheon had been manufacturing magnetrons for radar systems throughout the war. Spencer was standing near an operating magnetron when he noticed something strange. The chocolate bar in his pocket had melted. Most people would have just been annoyed about the ruined chocolate. Spencer got curious. He suspected the magnetron's microwaves might have caused it. So he did an experiment. He held a bag of popcorn kernels in front of the magnetron and watched what happened. The kernels popped. Spencer realized that microwaves could heat food rapidly and efficiently. On October 8, 1945, Raytheon filed a patent for a microwave cooking device. The first radar-range microwave oven went on sale in 1947. The early microwave ovens were huge, expensive, and mostly used in commercial settings. But over the next 20 years, the technology improved and costs came down. By the 1970s, affordable microwave ovens were appearing in homes across America and Europe. Today, there are over 1 billion microwave ovens in use worldwide. That same cavity magnetron design, originally created to hunt submarines, now cooks meals in over 90% of kitchens in developed countries. The cavity magnetron also revolutionized radar beyond military applications. Weather radar uses magnetrons to track storms. Air traffic control uses them to guide aircraft safely. Maritime radar helps ships navigate. Police radar guns enforce speed limits. Even some security scanners use magnetron technology. In 1949, the British government's Royal Commission on Awards to Inventors recognized Randall, Boot, and Sayers for their contributions. They shared a prize of £30,000, worth over £800,000 today. In 1945, they received the Duddell Medal from the Physical Society of London. In 2024, the IEE unveiled a commemorative plaque at Birmingham University, formally recognizing the cavity magnetron as a milestone in engineering history. But perhaps the most fitting recognition is this. Every time you use a microwave oven, you're using a direct descendant of that device, Randall and Boot, built in 1940. A device originally built to see submarines in the dark now reheats your coffee. A weapon of war became a tool of convenience. The magnetron that helped save Britain from starvation now feeds billions of people around the world. From a Birmingham laboratory to the Atlantic Ocean to your kitchen counter. From a desperate wartime gamble to one of the most common household appliances on Earth. That's the legacy of the cavity magnetron. That's the story of how one engineer's crazy idea changed the world twice. Once in war, once in peace. And that's how a small copper device, built with parts borrowed from a gun factory, turned the tide of the greatest naval battle in history.